Good morning. I am Krishna Kumar from Krishna's classroom. We continue with the recordings of the lectures on linear algebra. This is the 8th one in the series. 7 of them have been given and recorded at St. Joseph's College, Kozhikode. The earlier part of this year, before that went off for want to continue this series of lectures here. Now, the topic for today's discussion is what are called quotient space. It's a very important concept in mathematics. You would have heard of quotient groups, quotient space, quotient topologies, and all sorts of things. Okay. Now let me begin with an example to get a feel for the problem. So we begin with a very familiar and simple example, but which is very typical in the sense that it just tells you everything about the concept. So we take the example. Let X R2 over the field F taken as so R2 over R. You know that this is a finite dimensional vector space. Is two-dimensional. In this series of lectures, we will be mostly concerned with finite dimensional vector spaces. Now, the advantage of working on R2 or R3, which are what are called the prototypes of linear spaces, is that you can get a geometric feeling of the ideas that come out. Okay, so let us draw some pictures. Now what we call is that what are the subspaces of R2? The subspaces of R2 are now subspaces of R2 are 0-dimensional, vector 0, then 1-dimensional, all lines passing through the orbit. Two-dimensional so these are the possible subspaces of this vector space. You see that the 0-dimensional and 2-dimensional vector spaces or subspaces are trivial, and therefore we shall not look at them because you won't get much out of it as far as working out the quotient is concerned. But we assume we start with the subspace. Let set upon X R2 such that x equal to du for t belonging to R, u a fixed vector, non-zero vector, then M is the line generated by u r. Now we shall write x in a component form and t of course belonging to R. Therefore, you see that if you take t as the variable, then you see that this gives rise to x1 equal to tu1, x2 equal to tu2, and if you eliminate t between them, you will see that it's a linear relation connecting x1 and x2. So in fact, it is something of the form a1 x1. So m is such that u2 x1 minus 0, and clearly u1 and u2 cannot be simultaneously 0 because we are taking u as a non-zero. Okay, so you have so this is the equation of the line passing through the origin. Now this is obtained by eliminating t between the two equations. X1 is equal to tu1, x2 equal to tu2. I mean, this we have discussed extensively in the second and third lecture. So I just request you to go back to that. So M is a one-dimensional subspace. So if you let us draw some picture, it is interesting. It is something like a vector u, and x equal to t is, if you vary t, then you run over this line. So this is the line here, which is a one-dimensional space. Now we also recall the equation of all lines parallel to it. What are the equations lines parallel to it? Suppose you have a vector A. So let A you define as and A possibly may be 0, A may not be 0 and all that. Okay, now look at this one. So look at, let us define this M plus A. Such that x such that if you take A equal to 0, then you get back your line, the same line. Otherwise, what happens is that this represents a line, but this line is in fact parallel to the given line. Passing through the point corresponding to the tip of the vector. So this is a line. So M plus A parallel to M passing through A is A1, A2, the point A1. Now there is a unique line, and this line is uniquely determined. This is unique. By U and A. So I can just possibly call it M. Equal to the setup of X. X is equal to E plus E belong to you can actually show that this is a line that is essentially writing out, x1 equal to, so what you have is so this corresponds to two scalar equations. So you have x1 equal to tu1 plus a1, x2 equal to tu2 plus a2, two simultaneous equations. Now you can easily eliminate u1 and t between these two equations. These equations, we get the line with equation u2 into x1 minus a1 minus u1 into x2 minus a2 e2. This is once again of the form equal to clearly you see that a1 a2 satisfies this equation. So it's a equation of a straight line parallel to the given line, x equal to du and passing through the point a1 a2. So these are the sort of situation that you have. Now you vary A. By varying A, one can get all lines parallel to it. By taking different A's, you can get all lines parallel to it. Something like this. All lines parallel. The given line M U G. So we started with the line M, which is a one-dimensional subspace. Now we translated this through the vector A. We got a line parallel to it. In fact, by choosing different A, you can get all the, you can generate all the lines in R2 parallel to the given line. The point is just you choose A different. Okay. So all that is by the choice of A, you choose a point A1, A2. In fact, the line that you obtain is the one that passes through the point A1, A2 and parallel to the line x equal to 3. So that's the concept that we have. Make some observations. See, if instead of A, suppose you choose a point B on the line. So suppose this is F, M, U, this is M. Consider MUB. So let B belong to M. Then MUB is identical okay. What is the assumption that we have made? We have chosen a point on this line and then we have constructed MUB. You can show that MUB equal to MUA. I mean the two sets are identical. Okay. And what is the relation between A and B? Now you see that MUA B belongs to MUA and M is B minus A equal to some K U for some K fixed K belonging to R. This is geometrically clear because what you have is that this is A, B. Now we are taking B minus A, which means B you are taking as the diagonal of a parallelogram, A as one of the sides, and you see that the two lines B and A lie on the same line parallel to this, which means that this part of the line is parallel to the original line that we started with. Therefore, you see that what is B minus A? B minus A is a vector along the line x equal to TU. So this is your B minus A. So that complete the parallelogram. So this is the vector B minus A. Now B minus A lies on the line M or MU0. Therefore, you see that B minus A is equal to T1U or KU for some K belonging to R. Conversely, suppose B is such that B minus A is equal to KU for some K belonging to R, then you can show that every point on the set MUA is in MUB and vice versa. That means the two sets MUB and MUA are one and the same. Okay? Therefore, you see that what you observe is that if B and A are related by the relation B minus A is equal to TU, then MUA is equal to MUB, which means the description of MUA in a different form is possible by the choice of B, provided you choose B geometrically as a point on this line, and you choose B as the vector corresponding. If so, you see that B minus A becomes a vector on the line M U0, and which means that B minus A is a scalar multiple of U. That's the point. That's we have already outlined the proof of this. So this is the importance. So if you choose any B on this line, you can generate it. So the representation of the line parallel to the given line is not unique. As you already know, the representation of this line itself is not unique, because any scalar multiple of U also will generate the same line. Okay, I have had a very detailed discussion on this point on in chapters 2 or 3, which I don't remember exactly where I did, but certainly in chapters 2 and 3 deal with this kind of studies. Okay, right. So the consequence is that if B does not satisfy this condition, then of course MUA is not equal to MU. That's what I said. If you choose A differently, you start getting different lines. Now, you look at the whole family of lines generated. So, what is the scenario? The scenario is that you are in R2. You are given a line passing through the origin, which you know is a one-dimensional subspace of R2, and the point is that you get the equation of all lines parallel. Okay. So corresponding to each A belonging to R2, there is a line which is parallel to it. And you see that not all these lines are different. They are either parallel or identical. Okay. So they are identical. So for instance, MUA is identical with MUB, provided B minus A is a scalar multiple of U, which in turn tells you that B minus A is a vector that lies in M, the original subspace that we have chosen. So this much of ideas let us keep in our mind. And once you have clarity about this, now we can proceed further. So let us list them. So I will draw a fresh picture. Okay. This is A, this is U, and this is a line M. Zero. Now choose any A so let us take the collection of given name U0, which is a one-dimensional subspace of we construct sets of the type M, U, A, that is or X such that X is equal to U naught equal to 0 given and A belongs to for all possible choice of B. As we have seen that when you vary A, you keep getting all the lines parallel to this. And in fact, every line parallel to this can be obtained. Now one observes the following. We have already shown that MUA equal to that is one of the fundamental results that we have. Therefore, not all the lines that you generate using different A's are different, but some of them are identical. The important point is that either for B and A, for the choice of B and A, either MUA equal to MUB or the intersection between MUA and MUB is empty. So, given A, B belonging to R2, either or MUA is different from, I'll put it this way, intersection that means there is no point common to MUA and MUB. You know that both MUA and MUB are lines parallel to that. So this is the statement that MUA and MUB are lines parallel to the given line So either MUA becomes MUB or MUA and MUB has no common point at all. This is the picture that you have. Therefore, the elements of the collection MUA. So you take this collection. This collection has the property that either two elements of the set are identical or they are totally different. Okay? So look at this collection. That means all parallel lines of all lines parallel to the subspace M or 0 more specific. Make one observation. Want to make an observation? The observation is that the entire R2, the set R2, this is an observation. Every line, every point in R2 is on one of the lines. Exactly on one of the lines and not on two different lines. Okay? So because of this identification that MUA is either equal to MUB, it may be called MUA or MUB or MUC or something, provided this condition is satisfied. But this is something that you observe. So it covers the entire, so R2 can be written as the union of this collection of lines. So R2 is the all lines parallel. Out of which some lines are identical. So we say that MUA is related to MUB. So we are defining a relation if and only if A is A minus B belongs to Q. That is A minus B equal to, this is A minus B equal to KU for some Q. This is Q. So this is a relation, we are defining a relation. So all these lines parallel, there are infinitely many of them. We define a relation. Okay? So this defines on the collection of all lines M U A for A belonging to we want to assert is that this is, because of this. Or equivalently, okay. So we make this. So look at all the points in R2, we can classify them. Okay. And we have now a relation defined between A and B, since that A minus B is equal to K. So let us identify this. Now this why is an equivalence relation? Because you see that A is related to A. Why A is related to A? Because A minus A is 0 and that is certainly on the subspace MU0. This is reflexivity. That's the first one that we have. 2. A is related to B implies B is related to. This is symmetry. You see that this is a consequence of A related to B means A minus B belongs to MU0. And since MU0 is a subspace, if an element is in the subspace, then minus of that element is also in the subspace. So A minus B belongs to MU0 implies B minus A belongs to MU0, which in turn means that B is related to Now you see that A is related to B, that is the third property. A is related to B, B is related to C, implies A is related to C. Now this is easy because A minus B belongs to MA. So this implies A minus B belongs to MU0 this implies B minus C belongs to 0. M U0 is the subspace R2, which implies A minus B plus B minus C 0. So this is transitive. Therefore, you see that the relation A related to B for A, B belonging to R2 as defined above is A equals so it partitions the entire class of vectors in R2 into equivalence, disjoint equivalence classes. Hence, this relation, namely A minus B belongs to 0. Partitions. Classes. And what are the classes? And these classes are the lines that is the collection M because you know you have already seen that they are either identical or disjoint. If A is related to B, then MUA equal to MUB. Otherwise, they are disjoint, and that's the important. Therefore, you have now, written the entire R2 as the union of parallel lines or union of lines which are disjoint. Okay, and every point in R2 is on one of the lines and exactly on one of the lines. Okay, and so you have R2 is union of U fixed, of course. These are disjoint, that M is equal to B or empties. Now these are the two possibilities. So they are disjoint union of parallel lines. Now these are called cosets. related to or generated by line or subspace M U0 through parallel translation. That means now what we have is that this is the line. This is the line, this is the original line that we start with MU0. This is M. Now by varying A, you can get all the lines parallel. A. So by varying A, you can get all these. Okay. So we have a new collection of objects called MUA. Make some more observations. What are the observations that we make from R2? Make some observations that the description MUA is not unique. It could also be MUB as long as B, by choosing B such that B minus A belongs to MU0. Now that is the observation, that is one observation that we make. Now another observation that you make is the following. This is purely 0. Suppose this is MUA and this is XRT. And suppose there is another line designated by MU. Now you see that obviously, given these sectors A and B, you can add them. What is the rule of addition? The rule of addition is by parallelogram law. So you are adding them. Adding them means this is what, okay? Pictorially, complete the parallelogram with A and B as the sides and then choose the diagonal. And remove that. The diagonal vector of this parallelogram, this is A plus B. And therefore, this is now there is a line MU, this is called MU A plus B. So we make some loud thinking. The loud thinking is this. Can you write and can you introduce an addition? So we have fixed A, we have got MUA, then you have got MUB by fixing B, and then we found that there is a line MUA plus B, and this is given by, and we are asking the question, is it possible for me to introduce an addition between these parallel lines? Okay, an addition between these parallel lines, and write MUA plus B as MUA plus MU. Is this feasible? This is feasible because we have some handicap or something to be doing. Suppose you take an A prime. Okay. So let A prime R2 be such that M U A prime equal to M, which is equivalent to A minus A prime and so also B prime that is B minus B prime belongs to is equal to A2 U for some K2. Okay, that means we have two other descriptions. So MUA is described also by MUA prime. MUB is also described by MUB prime. So what happens if you take that? So you see you have A prime here. This is A prime. And suppose B prime is this. Now you check whether A prime plus B prime. Okay, let us complete the matter. A prime plus B prime, which turns out to be this line. So this is A prime plus B prime. So does this imply A prime plus B prime belongs to M P? This is the question that you are asking. Is this true? Let us investigate. When is A prime plus B prime is in M U A plus B? That happens provided A plus B minus A prime minus B, A prime plus B prime is some constant times U. Okay? So what is the meaning of this? This is A prime minus A belongs to is equal to A1. This is B prime minus B belongs to is equal to system equal to K2U for some n. Now this implies a plus b minus a prime plus b prime, which is equal to a minus a prime plus b minus b prime, which is equal to a1 plus a2 b. Okay, so this is equal to k for some k. What does this mean? This means that mu, see, this implies that that is observation. That whether you describe it using B, A or A prime, whether you describe this using B and B prime and apply our addition formula, you end up with the same set. Or in other words, you have an addition now, or M U A plus M U B is equal to M U A plus B makes sense. There is no ambiguity. So it is well defined. That is the sum between these lines is well defined. Well defined as MUA plus MUB equal to MU of A plus. Okay. So you can now add two lines, two parallel lines to get another parallel line. Okay. So from, you consider the set of all lines parallel to the given line MU0, you can introduce meaningfully an addition between these lines to get a parallel line, which you call MUA plus 1. Okay. Now what more? See, so you are sensing something. You get a feeling that these lines, collection of lines, could be turning out to be a vector space. Okay. Now let us just check whether we are on the right track. Okay. What is that? What do you mean by that? Take all these collection of lines parallel to the given line. You can define addition. Now you know that A plus B equal to B plus A. Therefore, M of A plus B, MU A plus B is the same as MU B plus A. So verify that. That means A plus B and B plus A generate the same line. And so also M that means associative. Or in other words, what you are saying is that M and you have M U also you see that MU0 serves additive identity. Further, given MUA there exists MU minus A such that which is also the same as MU minus A. That means this collection of lines do form a group with respect to the addition that we have defined. That is, the collection of lines parallel to a given line zero form a abelian group. With respect to addition. This is very encouraging because it says that the addition that you have defined endows this collection with a structure, and it's an abelian group structure. So we are on the right path to possibly defining a vector space. Okay. So let us take a look at the scalar mode. define the following. And lambda belonging to R define lambda A belongs to, therefore you can talk about hence defined mu0. So it also belongs to this collection of lines parallel to this one. So you see that if I were to define, okay, now let me try whether it makes sense. Okay. So let me define what do you mean by lambda times MUA? That means every vector in MUA is scaled by the factor. So a vector, a typical vector is x belongs to if and only x is equal to x is equal to T1U plus A for some T1. Some T1 now lambda x is then equal to lambda T1 U plus lambda. This is equal to T2 U plus lambda okay, and this essentially belongs to M it makes sense. You are having another scalar here, that's all. So what you have is this. So you take some arbitrary vector x plus, say this is your A. So this is x, then x plus A is this expression. Okay. Now what about lambda A? Lambda A is a scaling of the same vector. So this is lambda. Then you have got m lambda A is this line. So this is the vector lambda. Okay. Okay. Now let us work out this. What about lambda x? See, you take, see, this is, okay. See, you are taking a vector here. So this is tu. This, you are taking a vector x. X is equal to T1u plus A. So this is T1u. Now what do we do? We are going to multiply this by lambda. When you multiply by this by lambda, you end up with, this point is lambda T1. This is lambda T1. So this is actually lambda T1u plus what? Plus this one. So this is lambda T1u plus this one, and that's equal to, this is lambda A. So this is equal to lambda T1u plus lambda. This point is, okay, using parallelogram. So you end up with this. So that's what I want. So this I write as u plus. Draw the picture correctly, then explain. This is the vector A, this is the vector lambda. This is Tu, this is lambda T1. I mean, you can actually, use the similar triangles to prove this when you do the scalar multiplication. Therefore, you get this answer. So what you end up with is essentially a line parallel to it. Therefore, m lambda the line lambda. So you take MUA, multiply by, scale every point by lambda, you end up on this. Now this is the point. You take any point here, scale it up by lambda, then you are. So this is B is on this, then this is lambda, lambda B. So let us prove that. Okay. You have to show that this is well defined. Okay. Verify that minus A, that means A minus B equal to some K U. Zero. Then lambda times this is quite easy to prove because what you have U lambda A and this is equal to M U lambda B, which is equal to why do you get it? Because this implies that M U lambda A equal to M lambda B is equal to B. Zero. Okay? Okay? Therefore, you see that if A minus B belongs to M U0, then lambda times A minus B belongs to M 0, which implies M U lambda A equal to M U lambda B, which is equal to lambda M by our definition. Okay? Therefore, if A is related to B, then this is the result. So, irrespective of the representation of MUA, the parallel line, scalar multiplication will always end up with the same line. So, scalar multiplication therefore, now what you have? You have the collection M A on which you have addition and scalar multiplication defined. Because here we are taking lambda belonging to and with respect to this addition and scalar multiplication, this not only becomes a group but becomes a vector space. And scalar multiplication which are well defined on these parallel lines. This connection is a vector space. Okay, so we have constructed a new vector space. What are the elements of the vector space? So the elements of the vector space are the following. See, we have zero, all lines parallel. Okay, so this is A. Now suppose this is lambda, then this is equal to M U, end up with the line parallel. It will be very nice and illustrative to show that analytically you can do it. Analytically, because I have heavily used geometric intuition to work out this using diagram law of addition. But you can actually verify this. Okay? I just list out what exactly one should verify. Now, what are the properties? We have already seen that this becomes a group with respect to addition. It's an abelian group with respect to addition. Scalar multiplication is well defined, and then with respect to scalar multiplication, what all things we should have? We should have lambda of quite easy to prove. Okay? It's quite easy to prove because you see that this is equal to and this is equal to very straightforward. So you see that this collection becomes a linear space. The other properties can be easily verified, like lambda plus mu of 1 into 0 into 0. And you see that in the abelian group that we have obtained, what is the identity element? The identity element corresponds to mu0. Okay, mu0, because we had this property that mu a plus MUA and M these properties are very quickly verified, because what we have, the only thing that you have to verify is this is the definition is unambiguously given. Once the definition is unambiguously given, everything is nice. So you see that the collection MUA for A belonging to is a vector space this relation. Or this amounts to saying that you can meaningfully define addition of parallel lines, scalar multiplication of parallel lines. Addition is a binary operation, well-defined binary operation. Scalar multiplication of a line parallel to a given line always end up getting a line parallel to it. So you see that those two operations are well defined, and then all these nice properties of the vector space are satisfied. Therefore, this collection of parallel lines form a vector space. Okay? So that's an observation. Now, what happens in the case of R3? Let me just make a mention of what happens in R3 and then give you that. Okay. So let us consider the case, and after that we will formally do all these exercises in final dimension. Okay. So we consider the case of R. What are the subspaces? Subspaces are non-trivial subspaces are lines through the origin and planes through the origin. The lines through the origin give you one-dimensional subspace. Planes through In fact, you see that all proper subspaces of R3 are either lines through the origin or planes through the there are infinitely many of them. Okay? Now the same exercise works in this case also. You end up with, we start with a line passing through the origin, parallelly translate it, you get all lines parallel to it through the in R3, parallel. Likewise, if you take a plane passing through the origin and translate it through a vector parallelly, this every vector is translated, you end up with a plane parallel to it. So you get cosets, the cosets that you obtain through these translations are all lines parallel to that given line or all planes parallel to that given plane. Now once again, exactly as we did here, you can talk about addition of parallel lines, scalar multiplication of parallel lines, addition of parallel planes, addition of or scalar multiplication of parallel planes. And you can show that the collection of all parallel lines to a given line form a vector space. The collection of all parallel planes to a given plane through the origin form a vector space. Okay? Right? And there is more variety in this class. So in the next lecture, what I want to do is to give a glimpse of this in R3 and then go to the abstract generalization. Thank you very much.